Hi everyone, it's Mrs. Hanson once again. Continuing our journey in Chapter 2, we left off with the topic of isotopes. I would recommend that you have your periodic table still nearby. You should have a calculator nearby, and I want you to practice calculating with me when we get to our practice problems on isotopes. Let's begin by referring to isotopes as atoms of the same element that have a different number of neutrons. So, what makes one atom of the same element different, making them weighing different amounts, would be the number of neutrons inside of their nucleus. Remember that if they are indeed the same element, this means that they must have the same atomic number, because the atomic number gives the atom its identity. The proton number is exactly the same for every atom of each element. If I change the proton number, it's not the same element anymore. But I am allowed to vary the neutrons, giving the atom different weights. And let me model that. In nature, there are two naturally occurring isotopes for the element of chlorine. One of those is called chlorine 35. The total number of particles inside of that nucleus count to 35. Of the 35, 17 happen to be protons. The identity of the element comes from the atomic number, the number of protons. That would tell us that the remaining particles in that isotope would be 18 neutral neutrons. But in nature, there's a second isotope of chlorine that weighs 37 units. The isotope still is identified by its atomic number 17. To be chlorine, it must have 17 protons, or it's not chlorine anymore. This would tell me that the nucleus contains 20 neutrons, whereas the other isotope only had 18 neutrons. It does not change the chemical property, the physical property, the interaction of atoms in any way, shape, or form by varying the number of neutrons. It just weighs a little heavier with more neutrons. So two different isotopes in nature found for the element chlorine. The three isotopes of hydrogen are shown in these molecular diagrams. What are the three standard notations for the element hydrogen? We'll write them together. Now in the first picture, notice that it has, if this represents the nucleus kind of just blown up, all I see is a proton. Who is element number 1? The very first element, of course, is hydrogen. Notice it has just one proton and 0 neutrons. The only thing in the nucleus is a proton. 1 plus 0 is 1 for the mass number. Hydrogen 1 over 1 is the first of the three isotopes. In this picture, I count 1 proton, giving me the identity of the element still as hydrogen, but a total of 2 particles, so the mass number is 2. The isotopic symbol for hydrogen 2, which is known as deuterium, deuterium 2 over 1. And a little rarer, but there are a third naturally occurring isotope. Notice that it still has 1 positive proton because that's still hydrogen, but the total number of particles in the nucleus are now 3. 2 neutrons in that 1 proton give me a mass number of 3, and this is called tritium. 3 naturally occurring isotopes of hydrogen. They have the exact same proton number, and because they have 1 proton, you know they also have 1 electron, but they vary by the number of neutrons. The first had 0. The second had 1 neutron as pictured, and the last one had 2 neutrons. The only difference between them is the number of neutrons. Let's identify the mass number, atomic number, proton number, neutron number, and electron number for each of those, and there's 4 to do. So I think we'll go and kind of create a chart. We need a mass number, an atomic number, protons, neutrons, and electrons. Let's just kind of create a grid to answer these easily. The first example is SN 118 over 50. The second example is PT, all I see is 195. We'll come back to that. The next one is carbon 13 over 6. And then finally antimony, SB 121. Do you have your periodic table nearby? I'm going to quickly find mine. There it is. All right, we're ready to go to work. The identity of the atom comes from the atomic number. So I know the atomic number right off the bat is number 50 for the first element. SN standing for tin. Tin on the periodic table is number 50, SN. And by definition, I also know that there are 50 positive protons, and since atoms are neutral, they have 50 negative electrons. So those three columns can be filled out by simply knowing the bottom number. The top number we refer to as the mass number. And the mass number here is 118. As a matter of fact, we can just quickly say every time we had a top number provided, we now know the mass number that's given to us in the problem. So I'll just quickly fill out the rest of the red there. Now, going back to the row 1, if 118 is the total mass, and of those 50 are coming from protons, how many remaining particles are going to be from the nucleus? So when I subtract 118 minus 50, I get 68 neutral neutrons. Let's go to row 2. I see PT in 195, and that's all I'm given. So I have to use my periodic table and research the bottom number. Find PT on your periodic table. It stands for platinum, PT. It is in the 6th period in group, the 1 through 18, you can see it's group 10, but it's number 78. I wasn't given that. I had to go find it. So I'm going to write down that 78 is its atomic number, but I had to look it up, and I knew it because I knew the elemental symbol. And now I can fill in 78 is the atomic number, which is also protons, which is also electrons. 195 minus 78, and I get the total number of, I'm trying to write that over. I'll hit that quick, 195 minus 78, and I get 117 neutral neutrons. This example in row 3 gave us the atomic number as number 6. Therefore, I know that it's 6 protons, 6 electrons. 13 minus 6 gives me 7 neutral neutrons. And the last one, the element SB. No atomic number given, but with the elemental symbol, we can find it on the periodic table. The elemental symbol given there, its number, SB, is 51. You see it on the chart? Number 51 is the atomic number. Oops, that didn't come out right. And so therefore, based on knowing that, we know there's 51 protons and 51 electrons. 121 minus 51, and you subtract that with me, we get 70 neutral neutrons. That was easy enough. Kind of overwhelming maybe at first glance, but when we created the grid, it became very easy. What's an isotopic symbol For the isotope of platinum, that contains 116 neutrons. All right, so we need the periodic table. Find with me the element platinum on your periodic table. It might be a hunt and peck, but you got to find it. Platinum's kind of in the center. It's a transition element. Find nickel, palladium, underneath it is platinum. It has a symbol PT. And platinum is number 78. So its atomic number is found on the periodic table. I need that tool in order to locate that. Now to get the top number, we're going to add 78 protons to the number of 116 neutrons. 14, carry my 1. The total number of particles in the nucleus is 194. Let's determine the number of neutrons in each isotope. Letter A gives us carbon 14. Well, the elemental symbol of carbon is capital C, and when you see a hyphen and a number, it's giving you the isotope's mass number. So that's carbon 14. The bottom number we need to find on the periodic table. It's element 6. 14 over 6 represents the standard isotopic notation for carbon 14. And the second one, very similar, the element bromine. If I'm given the mass number of bromine as 81, we need the bottom number, which is atomic number, which I have to find on the periodic table. Bromine on the periodic table is element 35. So our isotopic notation becomes bromine 81 over 35. And let's practice one more together here on this page. Magnesium has 3 isotopes. So I know that I'm going to end up writing 3 elemental symbols in standard form for magnesium. The first contains 12 neutral neutrons. The next contains 13 neutrons. And the next contains 14 neutrons. For each of these isotopes, give the following information. All right. And then use it to write the symbol. Well, the first thing we need to do is find magnesium on our periodic table. Magnesium is the elemental symbol Mg. Where do you locate it? It's in the second column, third row down. It's number 12. Based on knowing its position as number 12, we now know number 12 is its atomic number, which by definition tells me that there's 12 positive protons and 12 negative electrons. Now, the top number is what we call a mass number, and that's the sum of protons plus neutrons, and that's our top number. So every single time we have 12 positive protons, this mass number would be 24 units. Here we still are adding the same number of protons. The identity of the element is 12. This adds to 25 total parts, so the mass number of 25. And here when I add 12 to 14, we get 26. We've written the number of protons for each, the number of electrons match for each, same number of electrons is 12. We've decided the atomic number is 12. The mass numbers were varied, 24, then 25, then 26, and we turned those all into standard isotopic notations. Let's do a little molecular art just to really bring this point home. Which representation shows an isotope of structure 1? Which representation shows a different element than the other two? Which element has the lowest atomic number? Before we can answer any of those, we need to identify the elements. I want to know the proton number in each of these structures. And knowing that protons are positive, I'm going to count the number of positive particles. I have 1, 2, 3, 4, 5, 6, 7, 8 positive particles in that first structure. Those are kind of the shaded blue atoms. 1, 2, 3, 4, 5, 6, 7 protons in the second structure. Do you count like I do? 7 blue atoms. And how about here? 1, 2, 3, 4, 5, 6, 7, 8 in the third structure. So that means the following. Notice that atoms of the same element have the same atomic number. Atomic number is the protons. That means structure 1 and structure 3 are the same, and structure 2 is different with 7 protons. Structure 1 and structure 3 are isotopes. I know they're the exact same element because they have the exact same number of protons. I didn't even bother counting the number of neutrons, but I can. 1, 2, 3, 4, 5, 6, 7, 8. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9 neutrons. So I know that they are the same atom because protons are the same. They're not exactly the same weight because I have one more neutron in that last structure. Number 8 on our periodic table, by the way, is oxygen. This would have a total weight of 16 particles with the number of protons as 8. Over here, 9 plus 8 is 17 total particles, but it's still oxygen. And here, number 7 is actually nitrogen. So I have a completely different element because I had one less proton. Total number of particles, 1, 2, 3, 4, 5, 6, 7, 8, 9 neutrons. 7 plus 9 is 16 as this isotopic notation for that atom. Good work. Okay, so now all of a sudden I'm going to introduce a next vocabulary word, atomic weight. And I'm going to tell you that this does appear on the periodic table. We just talked about mass number as being a whole number for a very specific isotope. We found it by adding the particles inside the nucleus, protons and neutrons. I'm introducing a new term called atomic mass or atomic weight. You will hear those interchanged. Atomic mass or atomic weight. It is the weighted average of all of the masses of the naturally occurring isotopes of a particular element. We take an average of all the different isotopes and report that average onto the periodic table. And that's why you see a decimal point. That atomic mass or atomic weight has a decimal point because we're taking weighted averages. How much does each isotope contribute to the total mass of all isotopes of carbon? So for instance, the atomic number of carbon is 6, highlighted in blue. The elemental symbol of carbon, highlighted in purple, is capital C. The atomic weight of carbon is 12.01. This is the average weight of all isotopes. Now let me kind of refer to this a minute and drive the point home with an example. In nature, carbon actually has 3 naturally occurring forms: carbon-12, carbon-13, and carbon-14. Carbon-14 you may have heard of in terms of archaeological dating. If you'd like to know how old an artifact is that you have found through an archaeological discovery, they will often perform an archaeological test known as carbon dating. They're describing how much carbon-14 has decayed through the thousands of years, and they can do an instructional analysis of finding that. But look at the average. The average of all of those 12s, 13, 14s, when you put all of those together, the average would be 12.01. So what I'm saying is, let's suppose in a box you put 100 carbon atoms. How much of those carbon atoms come from carbon-12, carbon-13, carbon-14? Obviously, the vast majority must be carbon-12, because when I average the weight of the others, it goes up a little. It goes up from 12.00 to 12.01. So you can see that both of these are minor contributors, and yet they do exist because they've actually changed the average from 12.00, carbon-12, the most abundant, up a little bit, 12.01. So I might have one carbon-13, I might have one carbon-14, but the vast majority, 98 others, are going to be carbon-12 in that particular box. If I take that analogy one step further, in nature, we said that there were two different varieties of chlorine. We had a chlorine-35 and we had a chlorine-37. Go to the periodic table and look at its average mass. Find that decimal point in the box of chlorine. Do you notice that it says 35.45 is the weighted average of all the different isotopes? This is called the atomic mass or atomic weight. This is what's found on the periodic table. Clearly, you see now, if we had a box and put 100 atoms inside of the box of chlorines, all of these atoms, 100 of them, the average weight is 35.545, I guess. Which one is the most abundant isotope? Well, clearly 35 would be contributing more to the average because I'm still averaging with the total weight of 35, and yet I've changed the decimal enough to know that there's a pretty good amount of the chlorine-37. I mean, in other words, it didn't change it by just 0.01 like these two guys did up here. It changed it pretty miraculously by a whole 0.5. So there's more of these isotopes of chlorine-37 than there would be in nature of carbon-13 and carbon-14. Let's practice calculating how to find the average weighted mass. Remember that we're using these two terms, and your book uses atomic weight. It's the only book I know that has done so because we prefer the word mass over weight in science. Atomic mass of the element, the weighted average. And I'd like to model how to perform one of these calculations. All right, how to calculate. In nature, we said that there are two different isotopes of chlorine, chlorine-35 and chlorine-37. When we weigh them, we get a mass measured in atomic mass unit. AMU is abbreviated atomic mass unit. Chlorine-35 weighs exactly 34.97 AMUs. Chlorine-37 weighs exactly 36.97 AMUs. The relative abundance of each isotope. In nature, chlorine-35 is 75.78% abundant, in comparison to chlorine-37, who in nature is 24.22% abundant. What would that average to be? Let's model it. So for each isotope, we're going to multiply the mass times its naturally occurring abundance for each one. So isotope number 1, we're going to take its mass measured in AMUs, and we're going to multiply it by its isotopic abundance. So I'm going to remind you that when we multiply, the percent sign has to be taken into account. So when I'm going to say percent abundance as a decimal. You'll do that for isotope number 2, or however many isotopes there are. You'll take its mass, measured in AMUs, and you'll multiply it by its percent abundance as a decimal. And then no matter how many you have, you're going to add those. So I'm going to put like little equal signs here. We'll add those together and get the average mass. Now let's model this with some actual numbers this time. Isotope number 1. The first mass of the isotope for chlorine 35 is given as 34.97 AMUs. I'm going to multiply that by its percent abundance, 75.78, but notice I need to do that as a decimal, so I'm going to emphasize how we do that. 75.78 over 100 changes the percent sign back to a decimal. That's why I have 0.7578. I divided by 100 to get rid of the percent sign and go back to the decimal form. The second isotope had a mass of 36.97 AMUs. I'm going to multiply it by the percent abundance as a decimal form. And just to remind us how we're getting the decimal, I take the percent and divide it by 100 to go from the percent back to the decimal form. Now, on your calculator, you're going to hit with me the following, and I'm going to use my Google calculator to just kind of show how we'll do this. All right, so I'll go 34.97, don't round, times 75.78 divided by 100, and that's me just moving the decimal back, equals. And you get a number, 26.500226. Write the entire number down, 26.500266. I won't remember. 34.97 times 0.7578. 26.500266. Write it all. Don't round yet until the very end when we consider sig figs. 36, oops, I wrote in the wrong place, didn't I? 26.5000266. Sometimes my pen just doesn't write well on the screen. Thank you for your patience. You can keep calculating. I'll catch up. Okay, let's try the next one. 36.97 times 24.22 over 100. And again, you can certainly just put that into your calculator as a decimal, but I'm, just wanted to emphasize that we're moving the percent sign to a decimal form. So you'll see me put it over 100 to remind you to do that. And I'm going to write this answer as 0.9541334. Add the two together to get the total mass. So that's still on my screen. I'm going to add the previous answer, 26.500266. And my calculator reads 35.4544. How many sig figs should we have? We should report with the same number of decimals as we started with, given to us in the data table. So I'm going to round. 35.45 is my final answer. What do you think? We just did a little calculation. Each mass multiplied by its percent abundance in decimal form, and then simply sum each individual's answer to find the total, and you'll have your final average mass. Not too bad. Want to try another? This time we're given the weight of copper with two different isotopes. Copper 63, who has a mass of 62.93, and its relative abundance is 69.17%. A second isotope of copper, called copper 65, has an atomic mass of 64.93 and a relative abundance of 30.83%. Tell me the average mass of the isotopes. Isotope number 1 was copper 63. Isotope number 2 was copper 65. Cu, copper 65. Let's find the average mass. So 62.93 multiplied by 69.17 divided by 100, or simply just write it in as decimal form. It depends upon how comfortable you are doing that. This solves to 43.52861. I am not rounding a single digit until the very end. Row 2, 64.93 times 30.83 over 100, and I'm going to write the entire screen, 20.017919. Let's add the two together. Are you hitting with me? Be my calculator buddy. And when I hit together, I get 63.5466. Now let's consider rounding. All right. Go into the data table and how many decimal places, how many sig figs for the original mass numbers. And you can see that there were 4 sig figs originally, 2 decimal places. So I'm going to need to round my final answer, 63.55 atomic mass units. We're working to solve average atomic mass. This example has 3 isotopes, but don't let that bother you. We'll just add together 3 answers instead of 2 like the previous. I'm going to encourage you to pause the video and try these on your own and then come back and see if we have a common answer. I think practicing by yourself is really the key for mastery. All right, welcome back. You're starting up your video lessons, and I was working quietly along with you, kind of solving each of our rows, mass times the percent abundance in decimal form. We're getting now ready to add the three isotopes together for the grand total answer. I'm going to add the 2.499, the 18.949701 to the last answer I had, and I get a grand total of 24.309.099. Don't leave any decimals off until you consider the very end, because it will help with rounding. We need 4 sig figs or 2 decimals. That means we have to look at this number. Indeed, we have to round up 24.31 atomic mass units. Calculating average weight of all the different isotopes found in nature for magnesium. How'd you do? I hope this is getting comfortable. We're working multiple examples for you. Let's try one more. Practice makes permanent, and it builds proficiency and speed. Pause the video. Only start it when you have a final answer you'd like to check. All right, welcome back. I was working alongside you. We've solved the first row, taking the atomic mass unit of isotope 1, vanadium 50 is what that element is called. Vanadium has the elemental symbol V. We found 0.124875. The AMU times the second percent abundance gave us 50.81265, and I summed the two isotopes to find 50.93752. I have to consider sig figs as my final operation. I need to round up, so 50.94 atomic mass units. Excellent work. Hey, these aren't so bad. We've been practicing hard in terms of calculations with isotopes. Let's pause our second video here, ending section 3. When we pick up, we're going to begin examining the periodic table a little bit closer. Come back when ready.